Welcome to Hidden Layers, where we explore the people and technology behind artificial intelligence. I'm your host, Ron Green. We're back kicking off the year with another Decoded episode. And as always, we're going to cover the latest news in the field of artificial intelligence. There's big news from NVIDIA, OpenAI, Google, Amazon, and much more. To help me cover it all, I'm joined by two of my amazing Kung Fu AI colleagues, my co-founder and distinguished engineer, Zizi Tsai, and VP of Engineering, Michael Warden. All right, Zizi, Michael, Happy New Year and welcome back.
Happy New Year.
Happy New Year. Glad to be back.
We're going to do another Decoded episode. This is our second year of the podcast. I'm really excited. As usual, just an enormous number of things to talk about. I'll kick us off. I want to talk about, I think this is not too controversial, that the O3 model from OpenAI is probably the biggest news that's happened in the last few weeks. It's sort of mid-January right here. This came out right before the Christmas break. It is I think, a pretty meaningful step forward on some really hard benchmarks, math, programming, and reasoning. And we'll talk a little bit more about the performance metrics and this and that. But a couple of things. It's O3. It just came out like 3 months after O1. So what happened to O2? I'm curious, do either of you know why there wasn't an O2?
It's a trademark thing, wasn't it?
Yeah, exactly. During my research, I was like, it's a trademark. So that's why we went right from O1 to O3. It's a pretty sizable jump. I don't think from a performance perspective that's too incongruent. So this is a bit of a meta thing, but it really kind of didn't get much media coverage. And I think it was a little bit of a marketing failure on OpenAI's part. I think they timed it too close to the holiday break. But within AI circles, obviously, lots of buzz, lots of intense study. So a few things. I want to really quickly explain why this is important and then dig into some of the details. So on the programming front, it achieved a Code Forces rating of 2727. So that surpasses the median International Olympiad gold medalist ranking. So it's literally it would be one of the top competitive programmers in the world.
Better than, wasn't Alpha Proof? Didn't they get silver or something like that?
I think they did, yeah. They were like right under gold. And then on the frontier math benchmark, and this one is really staggering because this benchmark, they try to keep it fresh, and they have math professors and researchers writing new questions all the time so that they're not in the training data set. It had really an unprecedented jump. It went from the former state-of-the-art being 2% accurate to 25% accuracy on this. And these are like PhD level math questions, exceptionally difficult math questions. And then lastly, there's a bunch of other metrics, but the software engineering benchmark, it again was state-of-the-art with a score of like 70, basically 72%. But what really got all the attention was its performance on the ARC challenge, right? And the ARC challenge is this sort of AGI benchmark set of problems that Francois Chalet put together. Actually, I think it goes back a few years, but it only really got traction and got some buzz in 2024. It achieved a 75% accuracy on that, which is staggering jump forward in sort of reasoning performance. So my first immediate reaction was like, okay, it's a little bit of a niche challenge. So my immediate reaction was, how do I make sense of this? What does Francois think about this? Yeah. Well, he immediately tweeted out, and I'm going to quote it directly because I think this is pretty cool. He said, "Today, OpenAI announced O3, its next-gen reasoning model. We worked with OpenAI to test it on the ARC AGI challenge, and we believe it represents a significant breakthrough in getting AI to adapt to novel tasks. It scored 75% on the semi-private eval in low compute mode, and we'll talk about what that means here in a second, and 87% in high compute mode. So it can be expensive in that mode. It's not just brute force, he says. And he says, these capabilities are new territory and they demand serious scientific attention. So, all right, a couple things here that I think are really important. One is, we've got the scaling laws, and are we going to tap out, doing more of the same, just bigger? Is that really going to get us anywhere? More parameters, more data? I think it's a reasonable question. And then we've seen the shift to inference time compute, things like chain of thought, giving the model not a fixed compute budget, but letting it iterate on its own responses to improve them and think about mistakes it may have made. Well, on the low compute mode, where it got like 75% correct, those were just, a few $100s. Actually, it's less than that, $20 in compute per task. On the high compute mode, it would spend up to $6,000 just to answer one question. Now, I personally don't have a problem with that, because I think,
cure cancer.
Exactly. Like, okay, exactly. Here's the Riemann hypothesis. Go solve that. But it is very much in line with the stats that OpenAI released back in October, November, that showed the scaling laws associated with inference compute mirror the scaling laws we're seeing on the training compute side. So I think this is a pretty big deal. But here's the question. Do we have AGI now? Is O3 AGI? No, I don't think so. If you go look at some of the ARC tests that have failed, they're pretty trivial. Like a human would be able to solve them, I think, pretty quickly. But I do still think that this is a very significant breakthrough, and it's demonstrating that even if we've tapped out, which I don't think we have on the compute scaling, there's a lot of juice to be squeezed out of the inference side. So I want to hear, what do you guys think about this? Any feedback on O3? Where do you think it's a good direction? Are you impressed? Are you unimpressed?
It certainly feels like a new dimension of scaling law, going outside of the pre-train and doing it at the test time scaling. I think that's very promising in my view. And speaking of ARC and François, I don't know whether you saw the news that François just started a new lab.
Yeah.
I think it's called India.
Is that
or something like that?
Yeah, I saw he just got funding to focus on AGI and safety. Right?
Yeah, and specifically he said, it's he's going to focus on system 2, like the test time scaling, and
okay.
I believe it's probably focused on the search based scaling. So like the monocolor search tree, the AlphaGo type of methods.
Yes.
Which is different from what people think that O1 and O3 is doing, because although the details, I don't think the details are revealed yet about how O1 and O3 are trained, but it sounds like they could be just LLMs that's generating thinking tokens,
right?
Chain of thought tokens without applying search.
Right.
So I think that's interesting too.
No, I think it's a really good point, which is, how far can you push just that sort of autoregressive approach with injecting thought tokens versus more sophisticated searches that are a part of that sort of inference compute side. I love it. Michael, what do you think? Any thoughts?
Yeah, I think people are quick. I mean, we're dealing with a lot of popular science sort of marketing chatter now that we're kind of in this era that we find ourselves in, which I think is great and inevitable. But I think a lot of people are going to point to this and be like, oh, AGI, it's time to replace humans. Let's do it. And I think that I just have a sense that this year, I mean, these capabilities are amazing. And I don't have a comment on the approach or algorithms or anything like that. It seems to be a very big leap for sure.
Right.
But I just don't think the promise is that we can just automate a lot of things. I think humans still need to be in the loop. I've heard a lot of people that are just like, oh, AGI, it's amazing. Let's go add them to the workforce. It's great. But I think that there's so much experimental runway. And although it feels like, we've kind of reached this amazing milestone we have, but there's still so much left to do. And I'm just excited more than anything.
I couldn't agree more. And, I wonder if when we actually hit AGI, it'll be like everything in technology. Everybody's like, well, who cares? I'm not that impressed, right? Because it happens slowly. It just won't be like black and white,
Yeah, it is good that we're moving the goalpost a little bit, because before it was like, oh, if anybody passes ARC, this is going to be amazing. That's AGI. And now it happened, and people are always like, here are all these asterisks. Maybe they didn't quite hit AGI.
Okay, so I do want to double tap on that just a little bit. I totally agree. And I think that too many people think that intelligence can just be measured along one dimension. And if you go back decades, if computers could play chess, then they would have to be AGI. And we see over and over and over again that it's possible for computers to do things like write poetry, but not have general intelligence, and on and on. So,
and the goalposts are moved again.
And the goalposts are moved over and over. I totally agree. Okay, but I'm still excited about it nonetheless. All right, Zizi, I'm going to throw it to you for the next topic.
So one topic that I have been watching a lot over the last couple of months is world models. And I wanted to talk about some new releases, especially the Cosmos world model from NVIDIA. It's an open weight model. I got my hand onto it and generated a few videos, including using a prompt like, "Hey, Gecko is doing a kung fu kick," and that's why kind of go to wipe check for new video models. So I want to talk about the world models and also talk about its relationship to agentic AI, which is a hot topic I think this year. So speaking of world models, so like last year, there are some exciting releases. Sora was out in the same 12-day release period of OpenAI, same as O3. So Google DeepMind released View 2 and Genie 2. One of them, the View 2 is a video generation model. There are some very impressive results that people share. It's not open yet.
Right. Can I ask you a question? Do you... I can't believe we're not going to talk about Sora much here, because we were all waiting for it so much. But I was a little underwhelmed. I thought by the time they released it, they would have more consistency in the output. And then Via 2 from Google looks more impressive. What do you, just real quick, what's your reaction? Are you more impressed with Sora or the Via 2?
From the video quality that's released so far, View 2 seems more impressive. Yeah. But Sora is already released, and I already tried a few prompts, including the kicking gecko.
Yeah.
The consistency is great. Like the background is dynamic, it's believable. However, it's not following the instruction very, very well yet.
Okay.
And in contrast to competitive, competitor models from all over the world, especially in China, I think, also several companies in the United States, they have really competitive products to Sora already. So yeah, this is kind of surprising as how quickly people catch up to OpenAI.
It really is. It really is.
And View 2 is very impressive. Can't wait to actually get through the waiting list and actually try it out. Genie 2, I think it's something similar, at a similar quality. We have seen some demos too. It's more of a, so when people talk about world models, it seems like people really mean video generation models.
It is very confusing.
Yeah, but that's kind of like the current focus. I think maybe it's because people are focusing on robotics and self-driving cars and trying to build out environments for the agents to collect data in the virtual environments.
And I think possibly it's also a little bit of the fact that to plausibly generate these videos, you have to understand so much about the world and how things interact and how light refracts and, how waves, propagate and all that type of stuff in water. So I think there's I guess my point is there's a little bit of a plausibility around calling it a world model, I think.
Mm-hmm. Yeah, absolutely. And I mean, videos are more impressive.
Yeah.
We are all visual animals.
Yeah.
So yeah, Genie 2. And then later, I think new this year, Cosmos was released by NVIDIA. there are some other related models like World Labs, Fibis, these new startup released the generating worlds. We saw some impressive demos that it kind of works like a video game, right? You can navigate, you can input the arrow keys, and then it will generate what it would look like if you move left, move right. There's also the navigable world models, which is a paper from Yan Kuhn and Trevor Darrow's group. And Snapchat also released a model called Wonderland. Sorry.
Oh, I haven't seen that.
Yeah, so pretty quick moving field now. I want to talk a little bit more deeper about the Cosmos. It's an open weight model. It's the models can be downloaded from Hugging Face, and it's really a series of models, video generation models. There's like 2B, 4B, 7B, and 14B models. You can prompt it with text. You can prompt it with video or both, and then the output is just the video. Is no other physical representations yet. It also comes with, and I'm quite excited about this. It also comes with a set of tokenizers for images and videos, because the tokenizers or the VAEs are very important to compress the high dimensional video and image data into more compact representation for people to train model on. And it comes with different flavors. There's a continuous tokenizer for image, discrete tokenizer for image, which you can plug in GPT trainers.
Okay.
Which is very neat. And then there are discrete and continuous versions of video tokenizers. The compression rate is impressive. They have 8x8 spatial compression rate, or 16x16. They have the two variants.
Okay.
So very impressive tokenizers. I think that will help the community train more great models.
Did you say there were some like single billion parameter models associated with that release?
I think it is a series of small to big models starting from 1 billion.
I'm stunned that you could have a model with that few parameters generate even anything remotely realistic.
Yeah, absolutely agree. Okay,
well, I love that stuff. I'm really excited. I think, if you look back at that, it's just, to my mind, it all comes down to what you said, the VAEs and how much can you compress and get that sort of, high quality embedding on the manifold. And that's going to determine almost everything downstream from there.
Yeah. And so I tried to generate a few videos. It is good at generating warehouses and roads, as you can imagine why. So it's pretty good for training like self-driving car or robotics in warehouses. When I try to generate the, I can show you the example. When I try to generate the kicking gecko.
Yeah.
I think the consistency and the vibe is there, but it didn't really follow. It's not. It's actually a bunny.
I would say that's not a gecko. Well, that's great.
Yeah,
that's cool. It was fun watching all those when you were sharing them through Slack.
Yeah, but the cars and warehouses are pretty impressive. I think this is the 5 second. This is from the 7B model, not the biggest model yet.
Okay, just 7 billion parameters. Yeah. Wow. Okay, that was pretty impressive. Okay, we'll probably overlay those videos on top of the video podcast so everybody can see them in real clear color.
Right. Yeah, that's my topic.
Awesome. Michael,
wait for
you're up.
All right, I'm gonna let y'all choose. Do you want to hear about biology or you want to hear about GANs?
Oh, I think GANs, because I can't believe they're even a topic.
All right, let's do it. I know, exactly. Yeah, the title of this paper that I want to talk through is called "The GAN is Dead." Long live the GAN, a modern GAN baseline.
Catchy title.
I know, yeah. All these catchy titles are so funny. I feel like scientists from yesteryear would be rolling in their graves if they saw all this. But I mean, it's great research and it's still valuable. So, but this came out, I think, about a week ago. It was a collaboration between Brown and Cornell, I believe. And we all know here at this table that GANs are really hard to work with. And I think even back, I want to say it was about 6 years ago, we were training a super resolution model to help with this OCR task where we were trying to extract text from really corrupted images. And it's hard. I mean, the training is really unstable. You have this mode collapse problem. You know, those are the two notorious problems with these things. We ran into that, and the industry always runs into that. And people have all but written them off in favor of diffusion approaches nowadays. However, these authors, this is exactly like the ConvNext moment, which I can't remember how long. That was fairly recent.
That was like 21. Yeah.
21.
22. Yeah.
Yeah, around there. But yeah, they're in the same vein. They're like, whoa, hold on. Let's not totally write off GANs. Let's revisit. I think I'm guessing we're going to continue to see this theme of old architectures and ideas kind of getting prematurely written off without complete ablation studies and really crossing our T's.
And really understanding why they had some of these issues.
Yeah, I think I would be shocked if we didn't see this come up in other areas of computer vision, natural language processing, whatever. But what they did was they went back and looked at all these tricks that people typically do to, train GANs. It's really hacky. I mean, they're just their own beasts. I should pause and mention the reason for that is because when you train a GAN, you're trying to optimize a generator that is trying to generate real, fake images that look real. At the same time, you have this discriminator that you want to get good at trying to distinguish between real and fake images. So that's why they call it an adversarial network. They have competing objectives.
Right.
And because it kind of sits on that razor edge, the training's really unstable and it's tough to get them to converge. They did 3 stupid, simple things. I think it's not.
I love stupid, simple things.
It's easy to love stupid, simple things. What they did was, and these are all not new, it's just a winning combination. So they took the relativistic GAN approach, which was, and I don't think this is a new idea. I think this is definitely more than 5 years old or so. But the idea is to, instead of looking at these networks independently, the discriminator and the generator, try to have one combined loss that ranks real and fake samples relative to each other rather than trying to distinguish between them independently.
Oh, like learning to rank type of loss?
Yep. Yeah, that's exactly. And the loss function looks shockingly similar to the original GAN formulation. But really you're just trying to, instead of teaching it to just move samples just right across the decision boundary, it's more like triplet loss where you're trying to widen gaps between them, or at least
force them as far apart together if they're not the same, and get them really close together if they are.
Yeah. So that makes the mode collapse problem all but go away.
Okay.
And then the other 2 things, they literally just added an R1, R2 gradient penalty on the discriminator.
Are you kidding?
No, just they look at the norm of the gradients and then add a term based on that and the loss, and then those 3 things turn out to just kind of fix everything.
I'm stunned.
Yeah.
Can't wait to try it out. Did they release their code?
They did. They released their code, and they released a few results as well that I'll talk through. So there's a data set called stacked MNIST where, I don't know if you all are familiar, they basically just stack every digit combination in the MNIST data set so that you get 1,000 combinations because it's 10 by 10.
I got you.
Like every combination you can get of digits. They
Gotcha.
turn into a mode. And then it's a test of mode recoverability. If when you go and generate a new wide distribution with your new network, can you recover all those modes? And in every case they did. They got all 1,000.
Wow.
And then they also tested this technique against StyleGAN2 and a variety of other generative models. And they scored it using this FID score, which for those that aren't familiar, you basically take the data in your training data set, and then you look at the distribution of the embeddings, and then you generate most of the time the same number of samples, but fake, and just randomly sample for that. And then you look at the distribution of those embeddings and compare the 2. So an FID score of 0 is perfect. You know, your new distribution matches the old one, or the fake one matches the real one.
Right.
And so you want this to be small. And they beat all of the GAN, like traditional GAN formulations that they tested against, including StyleGAN2, and even some of the diffusion approaches.
That's what I was going to say. How does it stack up against diffusion, though? And it's doing fairly well, or
presumably. I mean, it's getting this FID score on. They looked at faces, FFHQ, that data set, ImageNet, CFAR, and then stacked MNIST, and then all of those they were getting FID scores into like 2 to 3 range.
Okay.
Which is
Super low.
competitive,
Okay.
relative to those other techniques.
Yeah.
Damn.
I mean, anything below 10, our human eyes can even tell. So
Yeah, so
it's
it's great.
Very impressive.
And so it's competitive, but I think their whole point of this paper is, hey, don't forget about GANs, give them some love.
And just, do you know, architecturally, it's just really all the same, still, adversarial approach. They just really focused on the loss function for the most part.
Actually, the beauty of it is, historically, convolutional approaches were favored for the backbones in these, just because they play nice, they converge really easily, and it takes a little bit of the variability of the training stability away. But with this new formulation, they also were able to use more modern backbones and get them to converge.
Okay.
So their winning combination ended up being more like a ResNet sort of backbone.
Okay. Wow. Okay. That's really fascinating.
Yeah. If all the treatments are concentrated in the loss functions, that's pretty easy to bring in
exactly
to old recipes.
Yeah,
Super
exactly.
easy.
Okay. That's really cool. I did not know almost any of that. That's fascinating. Okay. I'll jump in next. I'm going to talk about a new model called DeepSeek version 3. This is from the company DeepSeek. This is a Chinese-based AI company, and this is really impressive to me. Really impressive work because, and I don't know if this is true, but they're doing some really amazing stuff with low parameter count and low compute. And I don't know if it's necessarily being driven by some of the import bans around NVIDIA GPUs or not, but this is exactly the type of work that I think is going to push the frontier on what we can do outside of just looking at scaling laws, right? So instead of, if you think about like Llama 4, which is being trained right now, and we've talked about this before, I think it's being trained on 100,000 H100s. They were able to achieve staggeringly impressive results without anything near that. So real quick, just a few technical things. 671 billion total parameters, but they used a really aggressive mixture of experts model. And so only about 37 billion active tokens are used. It's multi-head latent attention. And they did say that they use some internal O1 style reasoning model, synthetic fine-tuning data as well. But essentially all the compute, and they were pretty open about this, pretty much all the compute came in the pre-training. Okay. So net, if you look at all of their figures, it's estimated it was only about $5.5 million to train what I think is it's a frontier model, right? So that these prices are just going to keep dropping. It's stunning. And it's unbelievably cheap on inference. It's basically 14 cents to 28 cents per million tokens. And that's about as cheap as you're going to get for a model of this quality. The performance numbers are staggering. Almost 76% accuracy on the massive multitask language understanding benchmark. That performance exceeds GPT-4 and Claude 3.5 performance. Now, it's not on par with O1, et cetera, but this is very much apples to oranges. A couple more did fantastically on the Math 500 benchmark. It dominated with like almost a 91% accuracy. That's like significantly ahead of Claude 3.5 and ChatGPT 4. And in my opinion, this is an example that we are starting to figure out how to do more with less. And if you read the technical paper on this, a lot of the benefits, a lot of the way they've achieved this was through really sophisticated software engineering, right? The way they constructed the mixture of experts and the way the data flows through this model, not to mention some of the literally like the training work that they did across the GPUs to handle it in a very thoughtful way. Really, really impressed with this. And I'm hoping that this is an example of where we can approach both ends of the spectrum and achieve high quality results without it just being throw more money at the problem.
Yeah. I think this is actually a great counterexample to the famous beta lesson that the scale is all you need. It's just like, they did a lot of, I read a lot of posts about their optimization in like pretty low level CUDA kernel level
Exactly.
optimization.
That's right.
Their multi-head latent attention. That's also an innovation.
That's right.
Here.
Yeah, to reduce some of the compute needed. Yeah.
So design and smart engineering matters a lot.
Yeah, that's exactly right. Just, good old fashioned smart engineering can push things a long way. All right, Ziz, I'm going to throw it to you. What do you have for us next?
So related to 0103 series, it seems to be a new battleground now. It's OpenAI versus world again. So we have seen this before,
Yes.
GPT versus Llama and all the other open source models, DeepSeek. Now Sora versus all the other video models, and now it's the test time compute, and people are trying to replicate how to train such models. And generally, I think there are two ways that I've seen. One is search based, like the Monte Carlo tree search based, where you will have to run the model multiple times in a long chain of thought, but then you have a verifier. The verifier is not a human verifier; it's another model that will score and give a feedback, like saying, okay, it's good or bad, right? And then you do a beam search with such a verifier,
right,
to arrive at a good final solution. So search-based, and then the pure LLM-based, which seems to be what people think that 01 and 03 are doing. So there's this open source repo, I think it's called 01 Replication Journey. You can search it.
That's all.
Very explainable. I mean, yeah. So they have code and documents about how they kind of distill. So they do a distill type of approach. They take the chain of thoughts language tokens, or I mean just the language from 01, I think, and use that as a training data to train their models.
Okay.
Yeah. So that's one way. And then most of other models that I have seen, and there are small models, for example, the ACE Math and RStar Math, that are pretty good at math reasoning, kind of approaching the 01 level. I think already exceeds the 01 level of performance now. They use search-based. So, for example, the RStar Math, it's a paper that's recently.
I was really impressed with that paper, by the way. That was impressive.
Yeah, and they use base models like Q1 or Phi3 Mini 3.1b, and use and like tune on top of that by applying the kind of the Monte Carlo tree search. But one challenge with the Monte Carlo tree search is that sometimes you will need very detailed PRM or process reward models that are kind of like verifiers that will verify intermediate steps, and then you have to train such models. You have to label so many ground truths for intermediate step, which is not really feasible. So they have some clever tricks to kind of overcome that, and their performance is pretty impressive. It seems like they were able to improve the Q1 2.5 Math 7B model from around 60% of accuracy to 90%, and the Phi3 from 40% to 86%. And it's already surpassing 01 preview at that time by 4.5%.
That's wild with a model that size.
Yeah, so this is quite interesting. And
I love that.
Yeah, I just wanted to quickly share that and see if there have any comments.
I'm shocked because 01 was just announced 4 months ago?
Yeah.
Wow.
Yeah. What's the relative size of parameters? I guess we don't know exactly how big 01 is, right?
I know that's the problem. Is it's just too hidden there. Yeah. Well, I love that, ZZ. All right, Michael. What do you have for us next?
I think I'm going to use all of my airtime budget to talk through this one.
All right.
So if I'm just getting too into the weeds, let me know and we'll wrap it up here.
All right, you got it.
But this paper I read, it's called Learning the Language of Antibody Hypervariability. It was from MIT and ETH Zurich. And I think this kind of sparked a new passion for biology. in me because it's so fast. Like there's this problem that I had no idea existed that, and reading this paper, it became apparent that, yeah, I'll just run through real quick. So these protein language models that we always hear about, like AlphaFold, et cetera, they're really, really great at predicting structures of proteins, right? However, they're really great at protein structure that evolved at evolutionary timescales. So most proteins in the world, and if you're a biologist listening to this and I mess this up, let me know and I'll say sorry. And
Deal.
Yeah. But most of these proteins follow this long line of evolutionary history. So there's this kind of like smooth evolution that in nature, when you go look for these things, there are a lot of patterns that are easy for a model to pick up on. However, when it comes to antibodies, it's totally different because if you think about it, you get sick, an antigen enters your body, and your B cells have to go try to design antibodies in very short order so that you can fight this disease. It does this thing called, what is it called? Somatic hypermutation. I just learned that new word, a new phrase. But it basically will intentionally mutate itself like over and over and over again in a very short time scale and try to find the winning amino acid sequence that makes an antibody that targets that disease or infectious thing that's inside of you.
Okay.
And the problem with that is they get selected for in a short period of time. So they make these wild leaps in evolution and just kind of show up in the wild without any sort of like evolutionary history to show for. Does that kind of make sense so far?
I think so.
So so those subregions of these amino acid chains are just incredibly hard for even models like AlphaFold to predict structure on.
Because they're just so out of their normal training distribution.
Exactly. They're just kind of like wild corner cases, every single one of them.
Okay.
And it's easy to tell where in these amino acid sequences it's responsible for these particular structures, but these language models are terrible at picking that up. So what they did, and I still am trying to wrap my head around how this even makes sense, but what they did was, so they took these amino acids, these protein sequences, and they used an existing PLM, like a protein language model, and they'll embed them. But then they take those little subsequences that they know are responsible for these little like affinity regions that like attach to antigens, and they intentionally mutate it, like algorithmically, they'll mutate it, and they'll watch the embedding layer to figure out what parts are actually changing when they mutate that. And then they just throw away the rest of the embeddings. And then they use that for their downstream task.
Oh, interesting. Okay. Let me say back to you just a little bit. So they're essentially, I always think about this, like if something's outside the training distribution, then to me, it's like you've got gaps in your manifold that you've learned in your embedding space, or it's warped in some way, or it's discontinuous or whatever. And what you're saying is they isolated the parts of the embedding that were responsible for representing this sort of like hyper variable chunk of the amino acid sequence.
100%. That's exactly it.
Okay, awesome.
Yep. So then I say that there's not a lot of data. There really is a serious set of antibody data that they can train on. It's not nearly as sufficient as taking the entire protein library of the world that we have cataloged. So that allowed them to focus on this area that they know is a weak point for the model. And they do the usual bag of tricks where they have, multitask learning. There's this downstream model that's based on these foundational PLMs. But the cool thing is, after using that one little trick and a couple other things that would probably seem more obvious to us, they were able to design antibodies for fighting COVID-19. And the success rate of binding went from, in practice, what's usually about less than 5% up to 82%.
Incredible. All right. So, I'm super passionate about this idea of, combining AI with biotech and healthcare, and especially within genomics. That's exactly the kind of, out of the box thinking that I think is going to produce leaps and bounds advancements within, therapeutics in the near future. That is absolutely amazing.
That's literally what I wrote. Like the point I want to close on is that you can have machine learning engineers, AI engineers, whatever you want to call them, working in isolation. You can have biologists working in isolation.
Good point.
But whenever you combine domains,
Yes.
and you have people that are very proficient in either one, that's where really incredible innovation happens. And I hope that other industries learn from this.
Oh my God. I love that.
Absolutely agree. And I really love how they like go beyond applying the language model, the protein language model as is, or diffusion model as is, but find the causal relationship of, tweaking the input and see which hidden layers, which hidden representations change, and then just use those and remove all the noise. That really
It's pretty smart.
It really is.
deep understanding.
That was a great one.
Yeah, I've used all my budget here. I'll show
Okay,
you.
that's okay. No, this is great. I've got one more thing I want to cover. I'll make this relatively quick, but it's just too juicy to skip. So I want to talk about the Best Paper Award at NeurIPS this year. I know you both know about this. So, the AI field there's no shortage of drama in this domain. This, to me, is like the next level of drama, okay? So what happened was there was this, I think, really interesting paper. It's called Visual Autoregressive Modeling, Scalable Image Generation via Next Scale Prediction. As you and I talked about this a little bit, it kind of feels like a very natural and obvious idea. And this is, a generative model, long story made short. Instead of like most diffusion image generation techniques, it doesn't do it on a pixel basis or a patch basis. It actually changes scale. So it will generate an initial version of the image that is like 8 by 8 pixels. And then as it progresses, it will double and it will go to like 16 by 16 and 32 by 32. And it's essentially this, they call it sort of next scale autoregressive modeling, and it works fantastic. And what's really great about it is it's got this hierarchical autoregressive modeling framework where the image generation process is divided into a series of scales and computationally very stable, very efficient. And the results I've seen are astounding. I think that this is it's one of those things where it was like kind of just out there waiting for somebody to discover it. And it's almost a given that this would work. And I love the conceptual simplicity. Won Best Paper of the Year. That's a very, very, very prestigious award. And the lead author, Ke Tian, was actually fired from ByteDance just, I think, in October, something like that, September, just right before the paper was awarded. He was interning there, and he was accused of deliberately sabotaging other engineers' work, including purposely inserting bugs that disrupted the training of like foundational size large language models, and manipulating code and making unauthorized modifications. And so as this guy who's a lead author in this award-winning paper is getting, feted here, ByteDance has filed a lawsuit against Tian. They're seeking $1.1 million in damages, and they want an apology. And so I don't know what else to say. It's a great paper. It legitimately is. But wow, what drama, right?
This could be a Netflix show.
Yeah, I know.
How do you sabotage your competitors' training?
I know, exactly.
Sounds like something that's made up that'd be like in a Silicon Valley episode.
That's exactly where my mind goes, 100%. All right, Zizi. Okay, I'm done. Why don't you bring us home with your final topic?
The next scale autoregressive model is really, really interesting. Thanks for bringing that up. I really love it for the fact that, it just feels very natural for vision problems and also other forms of data where the zooming in, zooming out operation makes sense. It doesn't make sense for language. So, so the next scale autoregressive model is also belongs in the camp of autoregressive models. But for the language model is, always the next token. But for image, along this scale, that's, this dimension is unique to images and videos and such.
Yeah, I think that's absolutely right.
Really, really love the idea and hoping to build more training pipelines out of it. The only other topic I have is kind of related to the small models and efficient training runs. I've been watching this GPT-2 speed runs, and in November, I think in one of the previous episodes of us, we talk about some results of using GPT-2 architecture, very small model, like 100-ish million parameters, and at that time, to get to a certain quality, you train for, I think, 8 minutes. I think they just broke 8 minutes, like 7 minutes or so during November.
Which is insane already.
Yeah, absolutely. Like using H100, 8 of the H100 cards. Now I checked back, during the holidays I didn't check, but now I just checked back in January. The record is now below 4 minutes now.
Hey, what does that entail? What sort of training recipe are we talking about?
It's a bag of tricks. It's like, if you watch their Twitter or X feeds, there are several people, replying each other. Oh, here's my training pipeline. Here's my training log.
It sounds like GANs.
yeah, exactly. And it's a long series of tricks applying to basically everywhere in the training pipeline. Some are
monthly. Do you know how many tokens they end up training on?
I don't know the exact number. They use the Fun Web. Sorry, I forgot the exact name. I need to find it out and attach to the show notes. But yeah, they use a fairly standard benchmark that Andrew Comparsi started. So when he did the NanoGPT training run,
right?
So
is that just like one epoch through one time through the data? I mean, 4 minutes. How much could you get done? I don't know.
Yeah, I don't know how many scans of the full data, but it's quick.
Yeah, that is.
If you think about it,
if regardless of whether it's not completely optimized or whatever, if you can train a model, a language model in that amount of time, and it be useful for anything afterwards, that is incredible.
Yeah,
I totally agree.
I really want to try this. With the Cosmos tokenizers to tokenize into discrete token IDs. You just take a large video data set. I think people have already done that and uploaded the tokens to Hugging Face already, and feed that to the GPT-2 speed.
Oh yeah,
speed run training line.
But I get it, because you're saying because it can be used in those sort of discrete models with that version of the tokenizer.
Yeah, I tried that before. It works surprisingly well. It shouldn't work. I didn't expect it to work.
I agree.
It just works.
When you mentioned it to me, I was like, "There's no way that's going to work," and of course it did. Unreal. Okay, wow. Okay, we're out of time. That could not have been more fun. What a way to kick off the year 2025. ZZ, Michael, thank you both for joining me as usual.
Thank you so much. It's great fun.
Thank you for listening to Hidden Layers. This series is hosted by Kung Fu AI, a management consulting and engineering firm focused exclusively on artificial intelligence. If you have any questions or thoughts about today's episode, or if you know someone we should feature, please visit us at kungfu.ai.